We all at some point of time in our lives have wondered what the heck I'm solving this for. I mean, sure, some of us can calculate derivatives easily, but oftentimes this question of what are derivatives exactly have haunted all of us at some point of time. But what if I told you that derivatives are nothing but just ratios? Let us just explore that in this short video. Let's start by thinking why we need derivatives at first place. Like why even bother taking derivatives? Or even before that, let's think about ratios themselves and why ratios, how it is related to derivatives. For that, let's start at layman level first. Let's take ratio of 4 over 2, which gives us 2. This simply implies that 4 is 2 times of 2, right? Simple enough. No need to take other examples. Coming to the point, now all that ratio did is compare the value 2 to the value 4. That is one way to look at ratios, that they are means of comparison. Now coming to the point of how ratios are related to derivatives. With derivatives serving the same purpose, it adds further functionality, which is of comparing the relative change, that means taking ratio, between dependable quantities. We will get to what all this means as we progress further in this video. At very high level, what we want to do is compare the change in one thing to the change in other thing. That is, we want to take the following simple ratio, and that is what our derivative is. Now let's plot a linear function graph y equals to 2x and compare the change in two things. For that, pick any 2 points on the x-axis. If we take their difference, it gives us 2 minus 1 equals to 1. And this is our one of the two things which we want to compare. Now since this is a linear function for each value of x, there is a determined value of y. Let's see the corresponding y values. Taking change in y values gives us delta y of 2, and this forms our second thing, which is change in y. Now by taking ratio we can compare change in y with respect to change in x. And this right here people is our derivative for linear function, and we get the ratio as 2. Essentially, we got to know that change in y is twice the change in x. But there is a slight catch here. Someone acquainted with at least intermediate knowledge of derivatives can think how derivatives could involve discrete differences. Because we know derivatives as this formula and not this. The difference between them is that one on the right is the ratio of infinitesimally small change in x and y, and one on the left is the ratio of finite changes in x and y, that is, discrete differences. And yes, you will be right, they both are not the same, but for linear functions, no matter how much small or big steps you take, the ratio of change in y to the change in x is the same. Well, let's verify by changing the second point. At all points, no matter how big or small change in x is, the change in y is fixed in comparison to the change in x. Thus, we get a constant value when we take the ratio of delta y over delta x. And since this ratio for linear function is just a constant value, we can use discrete changes in place of infinitesimally small changes. Now let's deal with a nonlinear function. For that, let's plot a function y equals to e of x by 7. And similarly as we did with the previous function, let's choose two x values on input x-axis. Thus we have delta x of 2 this time. Also, let's plot corresponding y values on output y-axis. This gives us a delta y of approx 4. So again, let's take the ratio of delta y by delta x, which gives us 4 over 2 equals to 2. And let's join the 2 points that are there on the graph by a straight line. Thus the ratio that we got here is the derivative or the so-called slope of this red line that you see here. But this time can we say that this ratio delta y by delta x is also the derivative of the nonlinear function? It's not the case, right? Then let's see what's different this time. For that, again let's tweak the second point on the x-axis, and as my value on x-axis changes, the corresponding y value also changes as governed by our nonlinear function. But this time, as my change in x becomes large or small, the change in y is such that the ratio is no more constant, unlike previous case. Clearly we can see that here as delta x changes, the inclination of the line also changes, which means the ratio of delta y over delta x also changes. Again, let's see for what happened in our previous case, and this time let me join the dots on the graph with a different color line, so that it is visibly clear that as delta x changed, delta y changed in such a way that the line connecting 2 points on graph is changing in length but has same orientation or slope as our function has. But in case of second function, different delta x has such a delta y that their slope, that is the ratio of delta y by delta x, is not constant, and that is visually reflected by the change in inclination of this red line here joining the 2 points on the function. Ultimately, it suggests that if we take finite changes in x and thus finite changes in y, we are missing out information on change in x and change in y, that is between our chosen delta x and y. So what can we do for such cases? Well, what else we could do? Let's reduce the delta x further this time. Reduce it a bit more and more and more, such that now delta x is literally going to 0, and as delta x goes to 0, our delta y also is tending to 0, but not equal to 0 itself though. Once we do this, notice the red line of ours. It is now almost tangent to our function. So the ultimate takeaway from all this is that if we make our change in x tend to, that is go to 0, the change in y is such that the ratio delta y by delta x is the slope or the so-called derivative, as we learnt, of this red line which is being tangent to our function. And this is why, my friends, we say that the derivative of a function is graphically the slope of a tangent line at that point of that function. One point worth mentioning here is the significance of making delta x go to 0 is that we are able to capture the ratio of change in x and change in y at all possible points, so that we don't miss out on any information that is there in between. Now before wrapping up, if I were to sum up again that what derivatives really are on high and abstract intuition level, it would go like this. The world is about change. As humans, our mood changes, our jobs, our friends, our lives is all under process of changes. As of mathematics and physics of the world goes, the position of object might change, energy of system changes, time changes, and those changes in one quantity depend upon the some change in other quantity. One's change in mood might be dependent on how situation in his or her life arose before them. Similarly, one's object position might change differently with different change in time. Thus, we needed a mechanism by which we could compare those two relatively dependent changes that occur in between two things, which is accomplished by taking ratio between them. But halfway through we understood that we don't need just any ratio of any infinite changes, but rather a ratio of change that is defined at single point. And that is where the knowledge of limits coalesce with the concept of ratio to give us what we know as derivatives.